Tired of the same old rocks in your backyard? You might be sitting on a treasure trove. The rocks in your backyard could be worth more than you think. Across the United States, field surveys, environmental studies, and academic excavations have uncovered gemstones in unexpected locations. Suburban lots, abandoned orchards, and road cuts not far from home. This video features 10 real mineral specimens, each verified by geologists or research institutions and documented in backyard-accessible terrain. Some are durable, some are chemically unstable. Others appear ordinary until tested. None of these stones is mythical. None require mining permits, but each one tells a story of temperature, pressure, and time. And each has already been found by someone who wasn't looking for it. Join us as we identify the overlooked gemstones hiding in plain sight and explain how they form, where they appear, and what to look for next. Rank 10, Fluorite, the backyard crystal hidden beneath Midwest soil. About 20 minutes southwest of Bloomington, Indiana, a strip of unused land borders what was once a modest limestone quarry, decommissioned in the 1950s. In early spring, after a rainstorm loosened the upper soil, a local collector discovered a small crystal embedded in the clay. Its edges were sharply defined, forming a nearly perfect octahedron. At first glance, the stone was unimpressive, pale purple, dusty, half covered in silt. But its geometric structure and softness immediately suggested fluorite. Fluorite, or calcium fluoride, CaF2, typically forms in regions affected by low-temperature hydrothermal activity. In southern Indiana, these deposits are associated with ancient fault systems that once channeled mineral-rich fluids through the Mississippian limestone. The area isn't considered a fluorite mining district, and most samples are found incidentally, not through commercial exploration, but by careful observation of eroded sedimentary layers. Extraction here doesn't involve machinery. Hobbyist diggers rely on chisels, small hammers, and nylon brushes. Fluorite is notoriously fragile, cleaving along 4 directions with little resistance. Mishandling during excavation can instantly reduce a specimen to shards. The best finds come from weathered shale zones, where movement and time have freed crystals from their host rock without crushing them. Colors vary. In Indiana, fluorite appears in muted tones, purplish gray, bluish green, sometimes with faint banding caused by trace elements such as manganese, yttrium, or rare earths. Under shortwave UV, some samples fluoresce a faint bluish purple, indicating natural formation and lack of artificial treatment. The specific sample collected here was brought to a mineralogy lab at Purdue University. X-ray diffraction confirmed its identity, and elemental analysis ruled out the possibility of commercial sourcing. It showed no signs of dyeing, heating, or synthetic enhancement. In terms of gemology, the piece was moderately clear, but not flawless. It could be cut into a small cabochon. At local gem shows, a polished piece like this might sell for $30 to $80, depending on the finish and depth of color. Still, most backyard fluorite doesn't enter the gem market. It ends up in drawers, classroom kits, or research collections. In this case, the collector donated the specimen to the university's geology department. It now sits in a clear vial with a printed label displaying the date, coordinates, depth, and surrounding matrix type. It wasn't sold, it wasn't shown, but it was preserved. Backyard fluorite isn't rare in a global sense. Still, finding it uncut, untouched, and scientifically validated, just a few feet beneath familiar ground, reframes how we view the mineral world, not as treasure, but as evidence of time, pressure, and the Earth's quiet memory. While fluorite requires controlled excavation and laboratory verification to confirm its structure, other backyard stones leave far more visible clues, not in symmetry, but in their surface. Some appear fractured, coarse, and seemingly unremarkable. Yet once broken open, they reveal internal histories layered in color. Jasper is one of those materials, not defined by clarity but by complexity, and in certain dry zones of the American Southwest, it occurs more often than most people expect. Rank 9, Jasper, the patterned silicate found along dry creek beds. In the foothills of northern Arizona, along the arid edges of the Mogollon Rim, A sequence of alluvial fans carries mineral debris down from exposed rhyolitic outcrops. These fans, formed through centuries of flash flooding and thermal fracturing, often yield sedimentary conglomerates, quartz, feldspar, and occasionally cryptocrystalline silica. Among these, Jasper appears with frequency, though rarely with visual uniformity. No two fragments are alike. Jasper is not a mineral species in the strictest sense, but a textural variety of Chalcedony, itself a microcrystalline form of silicon dioxide. It forms through the silicification of fine-grained volcanic ash or sediment, often in the presence of iron oxides or manganese, which lend it its color and patterning. In Arizona, jasper is abundant near volcanic flows that cooled unevenly. Unlike opal or agate, jasper lacks translucence. It is opaque and dense, often displaying brecciated or orbicular patterns that reflect the complexity of its depositional environment. Most jasper pieces found in creekbeds are water-worn, their surfaces dulled by years of mechanical abrasion. Fresh fractures, however, reveal an inner polish, red, mustard yellow, ochre, or olive green, sometimes banded, swirled. These aren't accidental features. They're indicators of the geochemical environment at the time of formation. A high presence of iron turns the matrix crimson. Manganese contributes black veining. In some cases, fossil impressions or organic residues are preserved within the matrix, though these are rare. Unlike fluorite, jasper requires no lab testing for identification. A field geologist can confirm its identity by examining its luster, hardness, around 6.5 to 7 on the Mohs scale, and internal texture under a hand lens. It resists weathering well and can survive for millennia in exposed creekbeds. Commercially, Arizona jasper is used in cabochons and beads, typically hand-cut by lapidarists in the Southwest. The price range is modest. A well-shaped 30mm cabochon might retail for $15 to $40, depending on color contrast and symmetry. While some marketing labels it picture jasper or desert jasper, these terms refer more to aesthetics than to any distinct mineral characteristics. The stone collected during the 2022 field survey near Pine, Arizona, displayed multi-directional flow patterns and hematite inclusion halos, suggesting rapid silicification in a fluctuating, oxidizing environment. It now forms part of a comparative teaching set in the Department of Mineralogy at Arizona State University. The sample was not cut or mounted, as its surface patterns served a greater value as a reference than as an ornament. Jasper isn't hidden. It doesn't demand excavation. It waits in open washes, sun-scorched and wind-tumbled, alongside other fragments that never made it to jewelry. But for those who know what to look for, its color, weight, and silence distinguish it from ordinary stone. Rank 8, Garnet, the backyard stone, that entered the auction floor. In early 2021, a mid-size fasting lab based in Asheville, North Carolina, received a submission for pre-auction valuation. The item arrived in a clear hard case, without provenance papers, accompanied only by a handwritten note. Found this in my brother's backyard in Franklin County. Might be trash. The specimen was a well-formed dodecahedron, deep reddish-brown, unmounted. At first glance, it resembled almandine garnet, a common, inexpensive stone typically used for abrasives, but the structure was too sharp. The clarity is too high. A complete analysis was ordered. Garnet is not a single mineral, but a group of closely related silicate structures. The specimen tested positive for Fe3Al2S IO43, confirming it as almandine, but with unusually low inclusions and high light return. Garnet of this grade is rare in commercial parcels, but can appear sporadically in metamorphic belts, especially those associated with schist or gneiss. Franklin County lies within the western edge of the Appalachian Piedmont, where regional metamorphism has produced garnet-bearing mica schists for over 200 million years. In most cases, garnets from these regions are too dark, fractured, or embedded to extract cleanly. But backyard excavation, especially in zones near road cuts or natural erosion, can sometimes reveal liberated crystals. This particular sample likely weathered out of decomposing schist and was preserved in a topsoil pocket, protected from mechanical abrasion. Under gemological inspection, The garnet scored 7.5 on Mohs, displayed no dye, no heating, and exhibited low magnetic susceptibility, consistent with natural formation and minimal iron zoning. It weighed 3.4 carats pre-cut and was later faceted into a 2.1 carat cushion, brilliant with a 95% yield, an unusually high yield for garnet. At the time of listing, comparable natural, unenhanced almandine garnets of similar cut and clarity range from $60 to $120 per carat. This placed the piece at a conservative market value of $180 to $250, though it ultimately sold at a private bid to a collector of American-cut stones for $220. What makes this case relevant to backyard gemstone recovery is not the price, but the statistical rarity of quality appearing in overlooked terrain. Backyard garnet finds are often dismissed as industrial-grade rough, and yet this one passed 4 levels of certification: identification, enhancement check, provenance analysis, and optical grading, without a single note of modification. The cutter retained a portion of the rough material as a reference. It remains archived at the Appalachian Gem Review Center, labeled under Unsourced Domestic. No claim was filed, no lease signed. The original finder declined to list a name. Garnet is one of the few minerals that bridges the space between metamorphic science and commercial faceting, and in rare cases, between soil and auction house. This one just happened to travel that path. Rank 7, Agate, the silica shells buried beneath the orchard rows. In Marion County, Oregon, an agricultural remediation project involved soil core sampling across a retired apple orchard slated for conversion to a vineyard. The soil profile was primarily loam over basaltic bedrock, typical of the Willamette Valley. At a depth of 40 centimeters, the boring tool struck unexpected resistance. Not from rock, but from a dense nodule embedded in a weathered ash matrix. Once cleaned, it revealed alternating layers of milky white and translucent orange, with apparent concentric banding. Preliminary assessment identified it as agate. Agate is a variety of chalcedony formed through rhythmic deposition of silica within cavities of volcanic rock. The specimen stratification, evenly spaced bands with no visible porosity, suggested slow formation inside a vesicle from cooling basalt flows. These conditions are common in Oregon's tertiary lava fields, but few people expect agates to appear outside riverbeds. In this case, the piece hadn't moved in decades. Agates are chemically simple, silicon dioxide, but structurally complex. Under magnification, each band represents a subtle shift in mineral precipitation, influenced by temperature, dissolved impurities, and the presence of microscopic gas bubbles. In the Pacific Northwest, soil acidity and seasonal freeze-thaw cycles often fracture surface agates, making undamaged specimens more likely to appear in buried, undisturbed zones, like the compacted earth between orchard rows. This particular agate measured 6.2 centimeters in diameter and displayed approximately 22 visible bands. No dyes, no fractures. Spectrometer analysis confirmed the presence of trace iron and titanium, likely contributors to its soft, reddish-orange hue. It was manually polished on one face to confirm translucence, then cataloged for archiving. No market value was assigned, as the project fell under federal conservation compliance rather than private extraction. Agates in this region are commonly collected along rivers, especially the Santiam and Umpqua, where erosion exposes fragments. But buried agates, retrieved from fixed soil strata rather than alluvial drift, offer more insight into primary deposition. They're less tumbled, more intact, and retain their original orientation within the host rock. Lapidarists in Oregon often cut local agate into slabs or cameos. Lower-grade pieces sell as decorative rough for $5 to $10, while high-banding symmetrical nodules can fetch up to $40 to $60, especially when cut across the median. However, pricing is inconsistent and primarily driven by aesthetic considerations, rather than gemological rarity. The orchard agate was submitted to the Oregon State University Earth Materials Repository. Its GPS, depth, and core context were recorded, along with soil chemistry data. It was not intended for display or resale. It remains in cold storage, one of over 400 catalog specimens from the site, each a cross-section of volcanic history beneath cultivated land. Unlike gemstones marketed for their luster or investment, agate in its natural setting tells a different story, one of chemistry, time, and the quiet transformation of buried fluid into a solid structure, an unseen process until extraction. Rank 6, Serpentine, the weathered remnant found in road cuts and hillside slides. In Trinity County, California, a civil engineering firm contracted for a slope stability assessment ahead of a road realignment project along Highway 299. The area is situated within the Franciscan Complex, a geologic formation composed of metamorphosed oceanic crust and mantle rock that was accreted during Mesozoic subduction. Several test pits were opened along unstable roadside segments. One trench, approximately 1.2 meters deep, exposed a mottled greenish rock with a fibrous texture and a greasy surface luster. It was serpentine. Serpentine refers to a group of hydrous magnesium silicate minerals, most commonly lizardite, antigerite, and chrysotile, formed through the alteration of ultramafic rocks such as peridotite and dunite. In California, surface serpentine commonly results from the regional metamorphism of former oceanic lithosphere that has been uplifted and faulted into a complex topography. The sample was layered, pale green to dark olive, with a fracture pattern that followed topographic shears. The material was not intact enough for architectural use, but dense enough for geologic classification. Hand lens inspection showed typical serpentinization textures, mesh-like structures where olivine grains had been pseudomorphed by fibrous serpentine. A weak reaction to hydrochloric acid and a Mohs hardness between 2.5 and 4.0 confirmed the identification. No visible chrysotile fibers were present in this zone, though the team noted friable material farther upslope, where exposure had increased. In California, serpentine is recognized as the state rock, not due to its value, but because of its abundance and geologic significance. It is neither rare nor commercially prized in its natural form. However, when compact and fine-grained, certain types of serpentine can be carved or polished into ornamental items. These are sometimes mislabeled as noble serpentine or new jade in retail. Still, the market price remains modest, typically ranging from $10 to $30 per polished piece, depending on the pattern and luster. Serpentine often appears in backyard contexts where terrain intersects with fault-altered ultramafic belts. Road cuts, construction zones, or hillside erosion can expose weathered blocks previously buried under colluvial debris. In such conditions, specimens may be partially intact, though highly altered by chemical weathering. Surface hydration frequently results in a chalky outer crust, concealing the more stable green matrix beneath. The sample from Highway 299 was photographed, logged, and transported to a regional soil mechanics lab. Its classification contributed to a slope profile that determined risk for rotational failure along that segment. It was not retained for display, but included in the geotechnical report submitted to Caltrans. No request was made to remove or conserve the material. It remains unexcavated, exposed at the trench face, covered only by temporary netting. Serpentine is not a traditional gemstone, but in backyard conditions along faulted terrains, it appears frequently, not for beauty, but as a byproduct of deeper geological processes made visible by slope, pressure, and weather. Unlike serpentine, a product of mantle rock altered through deep geologic time, the next mineral is tied more directly to surface interaction. It doesn't require tectonic uplift or exposure to faults. It appears where water stagnates, where oxidation runs unchecked, and where modern construction often overlooks what lies just beneath rust-colored soil. For rank 5, the boundary isn't between ocean crust and continental plate. It's between metal and mineral, and how the two can mimic each other in surprising ways. Rank 5, Hematite, the metallic luster mistaken for iron scrap. In 2019, a suburban redevelopment plan in York County, Pennsylvania, initiated a soil audit across a former rail maintenance yard. The site had been inactive since the late 1970s, and much of the upper soil was compacted with urban fill, slag, rusted bolts, and concrete fragments. One object recovered near a drainage basin resembled corroded iron. oval-shaped, heavy for its size, and with a surface sheen somewhere between metallic and dull. But when scraped, it didn't flake. Underwater, it left a distinct reddish trail. The field team tagged it for further testing. The material was hematite, iron 2 oxide 3, an iron oxide mineral often mistaken for industrial debris. In its compact botryoidal form, hematite exhibits a steel gray to black surface, but leaves a red-brown streak when rubbed against unglazed ceramic. This streak test distinguishes it from both magnetite and metallic waste. In nature, hematite can form as a primary mineral in igneous environments or as a secondary product of iron weathering near the surface. In Pennsylvania, shallow hematite nodules are commonly found in Triassic red beds and oxidized zones of old iron workings. The sample was not from railroad operations. Petrographic analysis revealed a crystalline lamellar structure inconsistent with smelted iron. Its density, measured at 5.2 grams per cubic centimeter, is slightly above that of pure iron due to lattice voids. Magnetic response was negligible. Further investigation of the surrounding soil strata revealed no traces of slag or furnace residue within a 2-meter radius. It was a natural formation. Hematite is often overlooked in backyard settings due to its metallic appearance and weight. It lacks transparency and is not commonly associated with ornamental gems. However, when polished, certain nodules produce a mirror-like surface, known in lapidary circles as specular hematite. However, fragile along fracture lines, well-prepared cabochons sell modestly, generally in the $20 to $50 range, depending on finish and weight. Their appeal lies more in novelty than rarity. This particular sample was hand-polished on one face using a wet 1500 grit abrasive, revealing radial patterns consistent with low-temperature hydrothermal deposition. No inclusions were visible. The object was documented, photographed under raking light, and deposited into the mineral collection of the Pennsylvania Geoscience Archive for urban field specimens. While not traditionally valued as a gemstone, hematite holds relevance in backyard geology for one reason. It's often the first rock a non-geologist picks up and misidentifies. Its deceptive luster mimics metal. Its weight suggests an artificial origin. But hematite is neither scrap nor waste. It is a naturally occurring mineral that bridges environmental science, material history, and surface mineralogy. In transitional landscapes, where geology, industry, and erosion intersect, hematite doesn't always shine, but it endures. Unlike hematite, which often mimics industrial waste through form and density, the next mineral presents a different challenge altogether. It doesn't resemble metal, nor does it imitate debris. Instead, it shifts visibly depending on light, angle, and surface moisture. Rank 4 isn't defined by hardness or weight, but by instability. In certain wetlands, floodplains, and sedimentary basins, its presence is seasonal, its color unreliable, and its formation still partially debated. Rank 4, Limonite, the mineral that pretends to be a gem. In the Mineral Intake Division of the Mid-Atlantic Natural History Museum, objects arrive weekly from private collectors, hikers, and amateur rockhounds. Most are quartz, some are feldspar, a few are discarded slag, misidentified as volcanic glass. But one sample submitted in August 2022 stood out. It had weight, form, and a deep golden color, almost resinous under LED light. The submission form listed it as amber in iron coating. The sample was not amber, it was limonite. Limonite isn't a mineral in the strict crystalline sense. It's a generic term for hydrated iron oxide compounds, primarily goethite and lepidocrasite, occurring in earthy, massive, or botryoidal habits. It forms as a secondary product, typically from the chemical weathering of pyrite, magnetite, or siderite in wet, oxygen-rich conditions. The sample in question originated from a low-lying field near the Potomac floodplain, where groundwater oxidizes iron-bearing clays during periods of seasonal saturation. Initial examination under binocular scope revealed no organic inclusions, disqualifying any possible resin classification. The surface pattern was micro-pitted and fibrous, consistent with bacterial mediation during iron precipitation. X-ray diffraction showed an amorphous structure, confirming that no single crystalline phase dominated the specimen. Limonite has no defined cleavage, no refractive index, and no visible internal order. Yet it often appears in gemstone contexts, not because of rarity, but because of mimicry. When polished, limonite nodules can resemble tiger's eye, jasper, or even opalized wood. This visual ambiguity makes it a recurring inclusion in wire-wrap jewelry, often labeled as iron quartz or golden agate, neither of which is technically correct. In this case, the sample was sliced using a diamond blade, revealing radial fibrous banding beneath a hematitic crust. The color ranged from dark orange to ochre, with scattered black dendritic inclusions. No magnetic response. Specific gravity tested at 3.8, higher than typical quartz but lower than hematite. Market value based on size, 5.3 centimeters across, and polish quality was estimated to be between $10 and $25 depending on the application. It does not qualify as a gemstone by gemological standards. What makes limonite notable in backyard contexts is its accessibility and the high rate of misidentification. It often occurs in sediment-rich regions, such as abandoned farm fields, clay pits, and creek margins, and can be mistaken for petrified wood or stained chalcedony. Its softness, 1 to 5.5 on the Mohs scale, depending on the mixture, limits its use in faceting, but its color, surface texture, and high iron content make it visually compelling. The museum retained the sample as part of its public submissions archive. It was labeled Limonite Pseudomorph after Pyrite, Potomac Basin, catalog number MAMH-2022-184. No cutting order was issued. It remains in raw form, unmounted, unmodified, and available for classroom reference. Limonite doesn't shine under light, it oxidizes, and in that transformation, it records not brilliance, but process. Whereas limonite is often mistaken for something valuable because of its color, the following material is different. It's not confused with gemstones. It contains them. In fractured host rocks across mountain foothills and roadside cuts, one mineral doesn't announce itself through shine or weight, but through fracture halos, pressure seams, and thin bands of embedded crystal. It's found not in open form, but trapped, layered, resistant, and often revealed only when the surrounding rock gives way. Rank 3 Chalcedony, the hidden layer in fractured basalt. In late 2020, a foundation study was conducted on a parcel of land near Hood River, Oregon. The site was scheduled for a retaining wall installation to prevent runoff into adjacent farmland. Subsurface mapping identified tertiary basalt flows with known vesicular zones. Rotary core drilling reached a depth of 4.7 meters before intersecting a partially sealed cavity. The extracted core revealed concentric silica deposition with a smooth, waxy luster, characteristic of chalcedony. Chalcedony is a cryptocrystalline form of silicon dioxide, composed of intergrowths of quartz and mogonite. In this region, it commonly forms as a secondary infill in voids left by gas bubbles in basaltic lava. The slow percolation of silica-rich groundwater over geologic time deposits the material in layers, often with color variation caused by trace elements. This specimen exhibited a bluish-gray central mass with a faint reddish rim, likely due to the presence of iron oxide. The host basalt displayed radial fracture propagation around the Chalcedony pocket, indicating mineral infill occurred post-cooling but before structural deformation. The cavity lining had no botryoidal texture, suggesting steady-state deposition rather than episodic flow. No crystal points were present. The interior was massive, smooth, and non-reactive to hydrochloric acid HCl. Hardness was measured at 6.5 to 7 on the Mohs scale. Chalcedony in basalt is difficult to identify before exposure. Unlike surface nodules, which weather freely, embedded specimens are usually found in road cuts, construction sites, or landslide zones. In this case, no prior visual indicators were present on the surface. Only drilling revealed the pocket. Core analysis further showed that adjacent basalt contained no additional mineralization over the next 1.2 meters. Polished slabs from similar formations in the Pacific Northwest are often marketed under trade names such as blue chalcedony, thunder egg, or agate nodule. However, most are chalcedony without full banding. When cut properly, these materials yield cabochons with soft translucence. Market value varies by size, saturation, and finish. A well-prepared specimen of this size, approximately 8.3 centimeters in diameter, might sell for $40 to $100, depending on its color zoning and clarity. The extracted core was not commercialized. It was submitted to the Oregon State Department of Geological Survey under asset tag ORB 47CH 2020. It remains in their permanent archive, preserved in the original cylindrical section, stored at a controlled humidity level. Chalcedony is not rare globally, but its formation in closed basalt cavities means it often goes unnoticed until mechanical intervention occurs. It doesn't appear on surface scans. It doesn't fluoresce, but when present, it records the final stage of hydrothermal quiet, a sealed environment where silica resolved, settled, and solidified. In backyard terrain shaped by volcanic history, chalcedony doesn't rise to the surface. It waits inside fractures until the surrounding rock fails. Unlike chalcedony, which remains sealed until machinery breaks the host rock, the following material offers no such protection. It forms near the surface, in oxidizing zones, where it is exposed to water, air, and pressure. And unlike most stones on this list, it doesn't hide. It stains, marks, and bleeds into everything around it. For rank 2, visibility isn't the issue. Stability is. Rank 2, Azurite, the unstable blue that forms, fades, and fails. In a 2021 environmental monitoring program across northern New Mexico, field teams identified multiple surface anomalies along arroyos intersecting weathered limestone outcrops. Near a collapsed fence line southwest of Abiquiu, blue surface staining was observed at the base of a drainage gully. The coloration was initially dismissed as paint runoff from nearby structures. Sampling confirmed otherwise. The deposit tested positive for azurite, copper 3 carbonate 2 hydroxide 2, a basic copper carbonate formed through the oxidation of primary copper ores. Unlike more deeply formed minerals, azurite is a product of exposure to the elements. It develops in oxygen-rich zones near the surface, where copper-bearing rocks interact with water, carbonate ions, and carbon dioxide. In arid environments with occasional moisture influx, azurite precipitates as incrustations, nodules, or radiating masses. The sample found here formed along a fracture plane in a silty carbonate matrix with green zones of partial transformation, an indication of ongoing alteration into malachite. Azurite is chemically unstable. Under prolonged exposure to sunlight, humidity, or fluctuating temperatures, it slowly dehydrates and oxidizes into malachite, a greener, more stable mineral. In uncontrolled conditions, this transformation can occur within a matter of years. The collected sample had already begun color migration, as evidenced by surface dulling and the development of a green halo along the fracture rims. The deposit was shallow, only 18 centimeters beneath the surface, and no other copper indicators were found within the surrounding meter. X-ray fluorescence analysis confirmed high copper concentration, over 53% localized content, with no detectable synthetic contaminants. The color was deep ultramarine under neutral light, with conchoidal fracture visible along broken edges. Though highly valued for its hue, azurite's fragility limits its commercial application. Its Mohs hardness ranges from 3.5 to 4.0. It's rarely facetted. Instead, lapidarists prefer to stabilize, encab, or slice specimens for static display. Untreated nodules from southwestern U.S. locations occasionally enter the collector market at $50 to $150, depending on saturation, matrix, and completeness of the specimen. However, many degrade in storage without proper containment. The Abiquiu sample was removed under permit, placed in sealed archival-grade resin, and entered into the Southwestern Surface Mineral Program's reference bank. Its color has already shifted slightly in controlled conditions, consistent with prior behavior of azurite in non-hygroscopic enclosures. Azurite is one of the few minerals found in backyard conditions that records both presence and decay. It does not last. It transforms, chemically, visually, and structurally. until the original mineral is replaced. And unlike other stones, the transition isn't hidden. It's visible, irreversible, and expected. For a material as vivid as azurite, it offers no permanence. It's a marker of where copper once touched air, and where that contact couldn't be undone. Where azurite fades, fractures, and ultimately transforms, the final entry does the opposite. It persists through fire, erosion, compression, and the passage of time. Rank 1 isn't defined by color, luster, or size. It's characterized by resistance. In the places where glacial force met crystalline pressure, where sediment failed but structure held, this mineral still appears, not easily and never in clusters, but often alone, locked inside rock that no longer moves. Rank 1, Topaz, the resistant crystal trapped in pegmatite seams. In 2020, during an academic survey of late Paleozoic pegmatite dikes in central Colorado, a team from the Rocky Mountain Geoscience Research Unit conducted manual excavation along a known granitic outcrop south of Lake George. The site had previously yielded muscovite, quartz, and feldspar. However, this season, the group recovered a terminated orthorhombic crystal, transparent and colorless, measuring 2.4 centimeters in length, embedded within a feldspathic matrix. Raman analysis later confirmed it as topaz, aluminum 2 silicon 4, oxygen 4 fluorine, 2 oxygen, 2 hydroxide 2. Topaz forms under high-temperature, fluorine-rich conditions typically associated with evolved granitic pegmatites. Unlike silica-based minerals that dominate shallower zones, topaz requires concentrated fluorine activity during late-stage crystallization, often in cavities where pressure remains stable as volatiles escape. In this occurrence, the crystal was found within a myerolytic cavity flanked by clevelandite and smoky quartz. No deformation bands or cleaving fractures were observed. What distinguishes topaz from other backyard-accessible minerals is not visibility, but survival. It registers an 8 on the Mohs scale, higher than quartz, and resists alteration under standard surface conditions. Its presence in pegmatite seams at or near the surface is uncommon but not undocumented in regions such as Colorado, Maine, and parts of California, where historic uplift has exposed deep crustal material. The specimen's optical clarity was rated VVS2 under polarized light, with no detectable twinning. The density was measured to be 3.56 grams per cubic centimeter, and pleochroism was absent, consistent with the formation of colorless topaz under slow, uninterrupted cooling conditions. No heat treatment or irradiation signatures were detected. The sample was not faceted, it was retained in raw form for structural study. Backyard collectors occasionally uncover topaz in tailing piles or exposed pegmatite zones left from 19th century prospecting operations. Most are partial crystals, abraded, cleaved, or opaque. Intact terminations exceeding 2 centimeters with no structural compromise are rare and are not typically sold at the field level. When processed and cut, such crystals may reach $100 to $300 per carat, although colorless topaz trades at a lower value than imperial or blue variants. The Lake George specimen was deposited with the University of Colorado's Geological Corps Archive, accession number CUGEO 2020 TZ03. It was not entered into the market inventory. No gemstone registry listing was filed. Unlike other stones found in shallow deposits or as weathered residue, pegmatitic topaz represents a mineralogical endpoint, the crystallized product of extreme geochemical refinement under prolonged pressure. It does not fade, it does not hydrate, it simply holds. Of all the gemstones that might appear beneath residential soil or in fractured country rock, topaz is among the least likely and the least affected by time. If you found value in this journey through the minerals hidden beneath everyday ground, consider subscribing to support the work behind it. Every like and comment helps us continue producing well-researched documentary-style videos, grounded in science, not speculation. And if you're interested in where this series is headed next, the upcoming episode delves into forbidden gemstones once used in ancient technologies, stones that are featured in ritual tools, alignment mechanisms, and objects that have been long removed from modern circulation. It's not just about what the stones are, but why some were never meant to be used again.